But anyway, I am recording it again. So the second part to chapter 10, not chapter 2. In the previous chapter, I talked about ideal yield, aka theoretical yield, the target yield, that's what you're shooting for in an experimental reaction. You have the experimental yield, what you actually make during the experiment. And then we do have um, the percent yield. I just noticed something. I am not sharing my screen. So let me go ahead and share the screen. So many little buttons, right? And I have to make sure I remember everything. It's easier when somebody's watching to remind me, hey, I cannot see what's going on. Anyway, I hope you can hear me. I hope you can see my screen. We'll continue from here. Since it does show that it's recording, let me make sure it is recording. It looks like it is recording. Yeah. Let me make sure, considering what just happened. Yep, I am recording. I can go ahead and enlarge the screen because it's just me once again. So we're moving on so we can see how to figure out the ideal yield, the actual yield, and percent yield. Now remember, as far as questions are concerned, in determining the ideal yield, the way you figure it out is by performing a stoichiometric conversion. So you figure out ideal yield using stoichiometric conversion or the theoretical yield. We want to figure out the target. How much mass of product should we expect during the chemical reaction? To figure out that value, you use stoichiometry conversion, mass to mass, mass to moles, moles to moles. Okay? And then to figure out the actual yield, you can only figure that out using experiments. So it says right here, can be determined by experiment or experience. You can't do math to figure out the actual yield or experimental yield. Okay? Then finally, comparing these two, we're going to be figuring out the percent yield, actual over ideal times 100. Okay? Let's go ahead and work this problem out. Now, remember, with stoichiometry, you're always beginning with a balanced equation. So the question itself may not have a balanced equation. If it doesn't, go ahead, read through it. You can skim to get the gist of it. What chemicals are reacting? What are the products? If the products are not given to you, you have to figure them out yourself. Okay? So what I'm going to do with this question right here, I will select the question, make sure I'm selecting everything important, copy, and then I'm going to add a new slide. And that's where I'm working things out. Yeah, so right here, make this bigger, 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 right there. Okay, so I'm working on this. A solution containing 3.18 grams of barium chloride is added to a second solution containing excess sodium sulfate. So barium chloride and sodium sulfate. So I've written these out as chemical formulas. Barium sulfate precipitate. So we get barium sulfate. And then the other compound would be sodium chloride. Okay. So this is going to be aqueous. This is going to be, they said precipitates. Precipitates means forming a solid. So this will be a solid. This is going to be AQ. And this would be AQ. Okay. And then I have to balance the equation. With any stoichiometry, we start with the equation and it has to be balanced. I have 2 sodiums here. I'll put 2 here, 2 chlorines. So let me see. 2 chlorines, 2 sodiums, that's balanced. It looks like the whole equation is balanced. Okay. Now I have to place this somewhere. I mentioned this before in the previous lecture that to deal with the balanced equation and stoichiometry, you want to select the 2 formulas of that balanced equation that will be used in the stoichiometric conversion. We have 3.18 grams of barium chloride. That makes barium chloride the given because we were given its amount, 3.18 grams, right? So I've used this number, use this formula, use this here, and my whole equation is complete. It says here, calculate the ideal yield of barium sulfate. They want to know how much barium sulfate is made. So this is the wanted, and it will also be in grams of barium sulfate, okay? So knowing this is desired, I have my 2 formulas of interest. One is barium chloride, my given. My wanted is barium sulfate. I have to write my conversion factor conversion starting with barium chloride, ending with barium sulfate. So mass of given, grams of given, 3.18 grams barium chloride. Oops, I'm about to spell a word. I guess bowspring. Okay, barium chloride right here. And then remember, we have to use the periodic table conversion, which is the molar mass of the formula. Get the mass of all the atoms in the formula as written. So it has to be 1 mole. Because remember, molar mass is the mass of 1 mole of the formula, barium chloride. So one barium, 2 chlorines. Okay. Barium, group 2. There it is. 137.3. Find my calculator. Oh, it's a little dark now. 137.33 plus 2 chlorines, 35.45 plus 35.45. Oh, I didn't press plus. Okay. Oh my goodness, y'all. This is the difference. When I'm trying to do the lecture again and I'm already fatigued, I'll power through. 137.33 plus 35.453 plus 35.453. I'm double checking my work. Okay, get 208. 208? Yeah. Man. Hold on a second. Let me turn the light on because it's kind of hard to see what I'm writing. Okay. That helps a little bit. Okay, so I have a mass here of 208. Okay, 208.2 grams of barium chloride. And then I have the balanced equation conversion. With that, you want to relate the moles, the coefficient you have here for your given, to your wanted, right? Remember, it has to be 1 mole. The 1 mole comes from the balanced equation of barium chloride. I'm pretty much describing this in the molar amount. And then that relates to this number here, 1 mole of barium sulfate, right? And then we have 1 more conversion, which is 1 mole of barium sulfate. And then we have to figure out the molar mass of that. So barium sulfate will be, barium is 137 again, 0.33, plus sulfur is at 32, 32.1, plus 4 oxygens, open parentheses, 4 times 16, close parentheses, equal. So I get 233.43 grams of barium sulfate. Okay. Cancel out moles of barium sulfate, cancel out moles of barium chloride, cancel out grams of barium chloride. All the units cancel out except for the desired unit. As far as numbers are concerned, to simplify this, I write it as 31.8 times 1 times 1 times 233.43 grams of barium sulfate. That will be our unit, right? Divide by 208.2 times 1 times 1. Let's see what we get. Oh, it's 3.18. Y'all, we're going to make it. I just have to be extra careful because when I get fatigued, I make a lot of mistakes. And I'm ready. I can tell I'm already fatigued. I had to take a break. 3.18 times 1 times 1 times 233.43 divided by 208.2, and this gives me what? 3.56. Or 3.57. I'll just say 3.57. Let me erase this. 3.57 grams of barium sulfate. Okay, so in our experiment, this is the ideal amount. If we are able to hit this target, if we can go to the lab and hit this target, we are doing well, 3.57. Well, they say here, B, if the actual value, if you actually went to the lab, did the experiment, and you instead got 3.37, calculate the percent yield. So we didn't hit the target, but we didn't do bad. The percent yield is the amount we actually got, 3.37 grams of barium sulfate, divided by the amount that we wanted to get, but we missed the mark, right? 3.57 grams of barium sulfate, and then times 100. What percent is that? 3.37 divided by 3.57 times 100. Not bad. We still have 94.4% accuracy. We still have that percent yield. So the percent yield can be seen like a percent accuracy, right? How close are you to the target? The higher the percent, the closer you are. The lower the percent, the furthest you are. Now, this has nothing to do with the quality of the product. That's a whole different area, right? That's an area of purity. Okay, let's go ahead and move on and see. Oh, they worked it out too over here, so that advances me a couple of slides right there. Now remember, you have a limiting reactant and then you have an excess reactant. A limiting reactant, this should have been written down here. This reactant has so many definitions. One of the definitions is that it's a reactant that is completely used up in a chemical reaction. That's one way of looking at it. Okay, this is a chemical reaction that when the reaction is starting, it is present. When the reaction is over, you can't find it, it's gone. So it's completely used up in the chemical reaction. The limiting reactant also is responsible for determining the maximum yield possible. When the limiting reactant runs out, the chemical reaction stops. So whatever progress has been made by the reaction, that's pretty much the progress. So the amount of chemicals that got made in the product, that would be your maximum yield. So we are being told here, another thing, limiting reactants determine amount of theoretical yield. In other words, they help you get that target number. Remember the target product? Yes. The limiting reactant helps you to determine the target product. So how do we figure out conceptually what the limiting reactant is? So there's a certain point where you don't have any excess or limiting reactant. That is called the stoichiometric amounts. When you have stoichiometric amounts in a chemical reaction, that means you have the exact amount needed of both reactant for the reaction to be possible. This is called essentially having the exact amounts needed for reaction to occur or to be possible. Okay? And with these exact amounts, there will be no waste. All the reactants form products. When the reaction is over, there will be no reactants left over. So I'll say here, after reaction is over, all reactants are used up. Essentially, both reactants gets used up. Nothing is left over. There is no waste. So if you were asked to design experiments where there's zero waste, you want to have that in mind. No waste, no excess, no limiting. But if you deviate from these amounts, you start to have an imbalance. You have too much of one, too little of the other. So when you have too much, that's when you have the excess reagent. When you have too little, you have limiting reagent. Okay? So in that context, the excess reactant is the reaction that remains unreacted when the reaction is complete. We're told here, so let me give you guys an example, numerical one. Let me think of a scenario where elements is simply combined. So it's it's a little hard to see something very, very, very simple. So I will go with, let's say, H2 plus Cl2 to give us HCl, okay, like that. So in this case here, this is the simplest I can think of. We need 1 mole of H2 for every 1 mole of Cl2 to form 2 moles of HCl based on the balanced equation. That's what this means, right? 1 mole of each of these produces a product. Okay, now once we understand that, it just means you need to have equal amounts. So if I have 1 mole of this H2, I have to have an equal amount of Cl2. I also need 1 mole of Cl2. And how much, or based on the balanced equation, how much of HCl will be made? Twice the amount, so it'll be 2 moles. Okay? Let me start from chlorine this time. If I have 5 moles of chlorine, then based on the stoichiometry or the way we balance the equation, I will need 5 moles of H2, and that will make 10 moles of HCl. The relationship that we use in the balanced equation has to be respected. So what happens? So these relationships, by the way, are called stoichiometric amounts. They're balanced. It's what we expect. So knowing that the amounts have to be equal, if I say I have 10 moles of H2, but I only still have 5 moles of Cl2, then only 10 moles of HCl will be made. Why is that the case? Because all the Cl2 will react until it runs out. It will really try to react all of this H2 present, but it can only react 5 moles of the H2 to make 10 moles. And then in the end, this amount here is going to be 0. So let me go ahead and show you how this works. I think one of the questions you guys had is similar to this. You have 10 moles here. You have 5 moles here. And then here we have 10 moles. Okay, so if this is a scenario here where I deliberately picked uneven amounts, I deliberately picked non-stoichiometric amounts. This is our initial state, right? Initially, we have 10 moles of H2, 5 moles of Cl2, producing 10 moles of HCl. Okay, when the reaction is taking place, all of the Cl2 will react. So all of it will react. So when the reaction is over, at the end, we have 0 moles, 0 moles of Cl2 because all of it reacts and runs out. So we will call this the limiting reagent because it's the reactant that runs out. It's called reagent or reactant, same thing. What about this? Okay, when the 5 moles of Cl2 react, remember H2 and Cl2 amounts that react have to be equal. The 5 moles of Cl2 that react with 5 moles of H2. So we have 5 moles less and we're left with 5 moles when the reaction is over. So you can see here, when the reaction is over, we have 5 moles here, excess. This becomes the excess reagent because it gets left over, but it has nothing to react with. And then the product side, of course, you all see how this happened. In the beginning, there was nothing here. In the beginning, there was 0 moles. When it got made, it became 10 moles. So in the end, oops, I keep saying milliliters, 10 moles. In the end, we have 10 moles, okay? Yeah, so when the reaction is over, we have excess H2, hydrogen, we have 0 chlorine, it all got used up and it is not there anymore, and that is why the reaction ends because the chlorine gets used up. Okay, we're gonna see a similar thing here in this balanced equation. In this balanced equation, we are looking at the balanced equation, kind of like what I did here, but from a different point of view. We're looking at this balanced equation from the particulate level. Remember, particulate level is that kind of like the art form of chemistry. We're looking at chemistry from the picture point of view, but the particulate level specifically refers to the level of atoms. So it is a picture, but the drawings are of atoms and molecules. And that's called the particulate level. So let's see. We have here carbon, apparently it's in the gas form, reacting with oxygen to form carbon dioxide. Oh, another 1-to-1 mole ratio. Love those. They're very simple to explain. That means for every one carbon that reacts, we need one oxygen, right? One of each to form one product. This is even perfect. Okay, so we have carbon here, we have oxygen. You can see from the beginning we don't have enough of both, right? Because we have three carbons, ideally we want to have three oxygen molecules. We only have two. Now, if we could have three, we would have no waste, but we only have two. So each of these carbons will go off with one oxygen molecule to form carbon dioxide. Now, they show us an intermediate state, this middle part, bringing them closer together. So fine, I'll show it over here. Each carbon goes off with the oxygen to form carbon dioxide. The carbon kind of snuggles itself between the two oxygens, forms carbon dioxide. There it is, you have one. And let's say the other one forms over here. When this goes off with that, forming the second carbon dioxide right here. But this carbon has no oxygen to go to because all the oxygens that were available run out because we started the reaction with not enough oxygen, less than needed. So oxygen is a limiting reagent because we started off the chemical reaction with less oxygen than we will really need during the chemical reaction. And that makes this one here the excess reagent. So in a chemical reaction, really, for the most part, you usually have two reactants, right? And in order to have a limiting reagent, you have to have a minimum of two reactants. That way, the one that runs out is limiting, the one that's left over is excess. Okay, so minimum two reagents or reactants. Over here, you can see the unreacted carbon makes carbon the excess reagent. And of course, these are your products. And that's the end, right? So let me move on over here. Oh yeah, they show you the mathematical form of what's going on, kind of like what I explained to you guys, number of moles present, based on the picture, right? You count 1, 2, 3. They have 3 here. 2. The one that reacts, the 2 react. They react T minus 2. Since it's a 1-to-1 mole ratio, the amount of oxygen that reacts matches the amount of carbon that must react. So in the end, you end up having 1 carbon left over, but you end up forming 2 products and you have this. So you see, in the beginning, the product hasn't been formed yet, so the product will actually be 0. Okay, so let me continue from here. I did try to simplify the slides to make it a lot easier. Oh, with this one too, I decided to bring in an equation. So early on, we know what is what. Oh, I forgot. I think I had this from before. Okay, I simplified this to show you how to figure out the limiting reactants. We're told here, calculate the mass of antimony 3 iodide, SbI3, this one right here, that can be produced by the reaction of 129 antimony. And so what I'm going to do here is, let me go ahead and erase this, and then cut this, and move this to the next page. So of course you have the answer here because I try to clean up the slides, right? Make it look good and neater than what it was before. Okay, so right here, let me go ahead and post the image I just copied. Oops, too big. Scroll down. Right there. This right here is a balanced equation. 2Sb plus 3I2 to give us 2SbI3. Calculate the mass of antimony 3 iodide. This is what is wanted in grams. If they don't say in grams, assume grams unless they say something else. That can be produced by the reaction of 129 grams of antimony. So we're given 129 grams of antimony and 381 grams of iodine. Then we're given 381 grams of iodine. Okay, so let me tell y'all what not to do, okay? Don't look at these two masses and say, well, we only have 129 grams of antimony and 381 grams of iodine. We obviously have less mass of antimony, so antimony has to be the limiting reagent. It doesn't work like that, y'all. I mean, I tried, okay? I was that student. As soon as I saw something, I'm like, let me try to get a way around this. Yeah, it doesn't work. You have to do the stoichiometry. the mass stoichiometry will tell you which one is a limiting reagent. How does that do that? Okay, so we're about to do a mass to mass conversion. Mass to mass conversion is what we call stoichiometry. The mass to mass conversion converts the given amounts to the wanted amounts. But how does that give us the limiting reagent? We'll find out. The limiting reagent tends to make less product. Okay? Since we have two numbers and I call them both given, how do we tell one from the other? How about we call the first one given 1? We'll call the first one given 1. We'll call the second one given 2. So we're performing two stoichiometries. First one from given 1 to wanted. We'll start from here and here. Second one will be from given 2 to wanted. Okay? So I'll start with given 1 to wanted. In given 1 to wanted, let's see. I have to start with my given number, right? Given 1. 129 gram of SB. That's the formula, the number and the formula that goes with the number. I use my conversion. Remember, it's PT first. 1 mole of SB. And the mass for SB antimony is 122. I'm abbreviating. I'm writing this number up, y'all. Okay, and then I have the balanced equation relationship between the given and the wanted in molar amounts, right? So I have here 2 moles of antimony. I write this down here, 2 moles SB. That goes with 2 moles of SbI3. 2 moles of SbI3. There. Okay, then over here I have another PT conversion. This time it's the PT conversion for the other formula, the wanted, not the given, right? So it's going to be 1 mole of SbI3. We got to figure out its mass. Pull out the calculator because I ain't doing that by head. I can do it, but it'll take a little longer and I have to verify everything. Okay, SbI3, SbI3. SB is 122. I just literally did that, SB by itself. I3, open parentheses, 3 times. What's I? 127, 127, close parentheses. That gives me what? 503. 503 gram of antimony 3 iodide. Okay, remember the PT is the molar mass from the periodic table, and molar refers to 1 mole. There's a mass of 1 mole. So the mass goes with 1 mole, okay? And we have this here. I guess I can do the math right now. 129 times 1 times 2 times 503 divided by 122 divided by 2. And I get 531.9 grams of SbI3. Okay, next. Next. Let me do blue. I'll do a blue pathway this time because I have more time to think. The second one, we're doing the blue pathway. The blue pathway takes us from given 1 to wanted. Okay, from given 1 to wanted, we're now just taking the blue pathway. We're going from iodine to antimony 3 iodide. Okay, so I have to start with this number right here, which is going to be 381 grams of I2, 1 mole of I2. Again, PT first. What is I2? I just said 127, right? Times, is it 127 for real? I need to verify that. Times 2, 254 grams of I2, then BE. This time you're looking at the balanced equation relationship between the two, the given and the wanted that you're talking about or looking at right now. So in this context here, we have 3, right, moles of I2, and then 2 moles of SbI3. And then PT. Oh, it's the same. I forgot. It's the same wanted, so I can just copy here. 1 mole of SbI3, 503. This part here, I like it because I can coast. Right there. Okay. Okay, there. So this time around, I have 381 times 1 times 2 times 503 divided by 254 divided by 3. What do we have? 3 grams of SbI3. Okay? So they wanted to know what the limiting reagent was. You want to start by comparing products. So compare mass of products. When I compare the masses of a product, what I see is this is lesser amount. This is lesser, right? Lesser of the two. For that reason, this is what we call the theoretical yield. That would be this amount here, okay? So if you were asked, you would say theoretical or ideal yield is 503 grams of SbI3, okay? Well, which one of the two reagents or reactants produced that amount? It was I2. So for that reason, I2 is limiting reagent. So if you're asked limiting reagent is I2. Okay, final question. They can ask you, what is the excess reagent? Well, there's only two reagents. If one of them is limiting, by default, the other one is excess. So, excess reagent is SB. Okay, so from this one question, they can ask you three things. 1, 2, 3. Okay, so of course I wrote that already over here. This shows you how much they got, which matches what we got. So I cleaned up the slides because they had two different methods and a lot of words in there. So I cleaned it out so it's a lot more crisper, and hopefully you can navigate through this a lot easier. Okay, there we are. So, oh yeah, there is one more thing they want us to get. They want us to figure out, once we know what is excess, we said this is excess, then how much of it are we wasting? They're saying calculate the amount of the excess reagent left, aka how much of the excess reagent was really unnecessary and therefore you're wasting it and wasting money. We have to figure that out. Okay, so we'll do one more conversion, and I'll set that up right here, add a page. Okay, so for this one, I'm going to set it up close to this. Where's my balance equation? Oh, right there. Let me see if I can copy this. It will be helpful to have this over. Okay, I'll copy this down here. So to figure out how much is left over, since we're trying to conserve the chemical, I'm going to use the color green this time. We have to figure out the limiting reactant. We did that. It was iodine. So we're doing one more conversion, but this time we're going the green path. The green path starts from the limiting reactant and ends up with the excess reactant. So I identified I2 as my limiting. I'm going to my excess. So starting with my limiting, I'm ending on my excess. Y'all see the path? So in this kind of questions, you tend to have, so each arrow has its own mass to mass stoichiometry, right? And you can see it. The red one starts from SB, ends on SbI3. The blue one starts from I2, ends on SbI3. The green one starts from I2, ends on SB. And the green one is what you need to do when you're trying to figure out how much of the excess reagent are you actually wasting unintentionally, okay? So to determine amount of excess reagent, I'll even do the conversion in green to be consistent. We'll do one more stoichiometry starting from our limiting reagent, which I started from here, and then we'll end with our excess reagent, because in the stoichiometry, the formula you start with is the one that you have information on. The formula you end on is the formula that you're trying to get information for. Okay, we're trying to figure out exactly how much of the excess reagent did we need, and therefore how much are we actually wasting. Okay, so I'll start with this number right here. If 381 grams of I2 react, if all of the limiting reagent reacts, how much of the excess reagent actually also react? So right here, 1 mole of I2. You're like, oh my goodness, so many masses again, right? PT again. But here's the good news. I already have the mass from up here. I won't even figure it out. I2 is 254. Same number, 254 grams of I2. See, that wasn't that bad. Okay, and then balance equation. I have to use the molar relationship between the two formulas, this one here and that. Okay, since I2 is on the bottom, since moles of I2 is on the bottom, I have to write this 3 right here. 3, right? And then the other one is 2, so it's going to be 2 moles of SB on top. And this is going to be PT. Okay. Oh, yeah. Units, this cancel out, this cancels out, this cancels out, this cancels out. Now I need the 1 mole of SB. And I won't even look at my periodic table. I have SB somewhere here. 122 grams of SB. I just copy from there. See, I'm not doing new math. 122 grams of SB. So I got all these numbers from the other equations, and ta-da, I have it set up. Units cancel out, units cancel out. Let me go ahead and do my math. I have 381 times 1 times 2 times 122 divided by 254 divided by 3. Let's see what we got. Okay, we got 122 grams of SB. Yeah, I checked this twice earlier today when I was doing this session earlier. 122. Okay, so 381 grams of I2 reacts with 122 grams of SB. That's great. That's what this is saying. But how much do we have? We had 129. That was more than what we needed. Given 129 grams of SB, that means 7 grams are in excess, right? You have 122 grams of SB. This amount got used, right? Or reacted. So when you subtract these two, what do we get? 7 grams of SB. Wasted. Because it would just sit in the container, just swim around. And chemicals cost money, y'all. So this is wasted. But essentially, excess. We figured out the amount of the excess reagent, 7 whole grams. Okay. Okay, let me see. They work it out over here. They do the same thing. The initial amount, the amount that got used, the amount that got left behind, and we have that. And then we come to this point here and we have energy conversion. So remember with this part here, make sure you know the units for energy, the SI unit for energy, the conversion factor to go from joules to kilograms, meters per second squared. That's simple. I think it's very straightforward. You want to know this conversion factor from calorie. Please notice the 2 different kinds of calorie. This calorie here has a small c. This is the regular calorie, like the calorie in the lab. Okay? So this calorie with a small c is the calorie in the lab. When we're doing experiments, we tend to measure the amount of energy in joules, but sometimes they use calories, and it's a small c. Now, when you have food calories, the C is big. You see that? This is a big C. This is a small c. You're thinking, tomato. It's a huge difference. A food calorie is different from a thermochemical calorie. Thermochemical calorie is a calorie that you get from a reaction in the lab. Food calorie is the calorie they report on a candy bar. Okay? So if they say a candy bar has 250 calories, big CAL, what they're really saying, okay, what they're really saying is this. The candy bar really has 250 000. Yeah, you heard it. Energy calories. So my brother traveled to Germany one time and then he brought me some German chocolate. So I'm like, okay, thank you, German chocolate, right? This is good. I'm gonna, eat some. I turned the chocolate bar over to see the calories. They do not report their food in calories. They use kilojoules, you know, Europeans. And that's what they use in my country too, kilojoules. I had to learn calories. I'm like, Americans gotta be different. Okay. So I'm looking at this and I'm like, 250,000 kilojoules of energy is in one. I said, I am eating one little square. So I ate the one little square, packed it up, and put it in the refrigerator. It took me over a month to eat that chocolate bar because I am like, I'm not eating the whole thing and getting multiples of this, right? But you know why they do the big C here. So the big C here, essentially, one food calorie is the same thing as 1,000 of the regular calories. That's how they do it. Because manufacturers here figured if we write 250,000 calories, which is the true energy value in that Snicker bar, I haven't had one in a very long time. Anyway, people will not eat it. They won't buy it. And we want them to buy. We want them to eat, right? We want them to buy, we want them to eat. So we'll use a big C. Nobody has fought it, so they keep using the big C. I mean, yeah, I'm just telling you what's out there. And then of course you have this conversion factor here. Just be aware of the conversion factors. You go from one point to another. You don't know how to do that. Here they're showing you, let's see, calculate the number of kilojoules, calories, and joules that are equivalent to 42.5 kilojoules. So here, let's see. Yeah, I feel like there's a lot going on here. But let me see if I can write it here with a brighter color, red. If we have 42.5 kilojoules, and our first conversion is to get to kilocalories, you want to have the conversion factor. So let's see. Oh, we do have a kilocalorie to a kilojoule. That's the number over there. Okay, so 1 kilocalorie equal 4.184 kilojoule. Great. Write the given number, 42.5 kilojoules. And then, where was I? Oh yeah, use this as the bottom number, 4.184 kilojoules, and then 1 kilocalorie. Ta-da! The kilojoules unit cancel out. You end up your answer in kilocalories. Oh, they kind of worked it out over here. I see it now from here to here. And we should get 10.2, right? So this is the conversion factor you need. Just one step conversion to go from one to the other. And then once you have that, you got this right here, kilocalories. Then to get from kilocalories to calories, you start with 10.2 kilocalories. You know, 1 kilocalorie is 1,000 calories. So take 10.2 times 1,000. Yes, I'm using my calculator just because it makes me feel good. Calories, right? Well, they got that here. And then what else? So we solve for this, we solve for this. And then joules, to go from calories to joules. Oh, I guess if you already have kilojoules here, right? If you already have kilojoules, if you have 42.5 kilojoules, to go to joules, just take 1 kilojoule times 1,000 joules. This and this cancels out. You get your answer, 42.5 times 1,000. I have 4250 joules, right? So I've done joules. Oh, here's the answer. They got joules. They got the calories. They got the kilocalories. One more. Oh, that's it? Yay, we got all of them. We got that there. We got our joules. We got our calories. We got our kilocalories. We got them all. Okay? Okay, let's see. So for thermochemical equations, this is the kind of the wrap up for stoichiometry. Stoichiometry is actually a lot bigger than what we cover. It covers a lot more different areas. This class is an intro class, so we're just kind of stepping into different topics and then we kind of step away to something else. Okay, so we're now looking at stoichiometry where heat is involved. So these are called thermochemical stoichiometry. You have equations that where there's a heat being transferred. So we're told the quantity of heat transferred in a chemical reaction can be measured in the laboratory. You know how they figure out calories? By figuring how much energy it takes to burn all that food. That's when you're trying to lose weight. They tell you to burn the energy. When you're burning the energy, you're essentially burning the food. It's kind of a very very layman way of saying it, but you're burning fat. You're forcing the fat to go through a chemical reaction, and when you do that, you process fat, consume it, convert it to carbon dioxide and water, and you breathe it out and pee it off, right? So we're looking at chemical reactions here that are either requiring energy or producing energy, right? The change is called heat of reaction or enthalpy of reaction. The more common term is enthalpy. Don't confuse that with empathy, okay? It's not feeling. It's enthalpy of reaction. The symbol is delta H. Now, your symbol here has a little bit more going on, so it's a delta H. Delta means change. H is the symbol for heat, okay, the heat of the reaction or enthalpy. So they tell you change indicates the fact that the amount of heat is changing. H is the symbol of enthalpy. Enthalpy is the heat content of a chemical reaction and the amount of heat that's been transferred. Okay? And then R here, the little r, stands for the chemical reaction. Okay, now that we define the symbol, we're told during exothermic reaction or during exothermic change, the enthalpy of the system goes down, and so delta H has to be negative. In other words, remember exothermic. Exo means that the energy is leaving the system, right? This is how I remembered it when I was a kid, because I was learning this in middle school. Okay, middle school, I barely really know vocabulary that much, barely hit puberty, and I'm learning this stuff. So I'm like, wait, exo sounds like exiting, so energy is leaving the system. The part I struggled with was the sign, because I'm like, how is heat leaving negative? Like I can't relate to that in my life as a teenager. I can't relate to this. So at some point in my journey, I decided, you know what? I need to find a way to learn this. So I thought about money. I didn't even know how I thought about it, but it just came to me that I thought about money. Maybe just talking to somebody. When money is leaving you, that's a negative thing, right? If you have to pay, I'm not saying anything negative against paying bills, but when money leaves your wallet, when money leaves your account, it's negative. Even accounting wise, that's negative. And I got a D in account in elementary school. These are all like my past, okay? Yeah, I never took accounting in college, but anyway. In accounting class, when you were spending something, it was negative, right? And maybe that's where I got it from. Anyway, when heat is leaving the reaction, that's negative. Terms that are used to describe heating or leaving, sorry, in an exothermic reaction. So let me go ahead and see. I'll describe it down here. Negative, once again, leaving the reaction, not a good thing. In the endothermic reaction, opposite of exo, heat is coming into the reaction. You're getting paid, you get a bonus, somebody just gives you money. That's a positive thing, right? Positive. So understanding it that way really helped to help me really understand this conceptually. Okay. Okay. Now, in one of your homework questions, I looked over that today, you're asked to write the thermochemical equation in more than one way. So we're told here, when you burn 2 moles of ethane, this is ethane right here, and you're burning 2 moles, 2855 kilojoules of heat is given off. So they're asking you, oh, by the way, burning is the same thing as a combustion reaction. You should have learned this in chapter, I think, 8. Burning equal combustion reaction. And the combustion reaction you usually have, for the most part, 95% of the time, you have 4 parts to 4 formulas in the chemical reaction. You essentially have, in the combustion reaction, this format, okay? I like formats because it helps you recognize things, right? In a combustion reaction, you tend to have a compound and element reacting to form a compound and a compound. So in a combustion reaction, you normally have a compound and an element as reactants reacting to form a compound and a compound. The compound tends to be a fuel, so it's some kind of organic compound with carbon and hydrogen compound. The element tends to be oxygen. Oxygen is required for a fire to burn. You have no oxygen, you have no fire. In the products, you usually get carbon dioxide and then you get water. And these are essentially compounds. Okay? So you got compound, element, compound, compound. Okay, so one of the ways you write the chemical reaction. Oh, I forgot to also say chemical combustion reactions are all exothermic. Okay, it makes it a lot easier. Combustion is exothermic all the time. If you've had the privilege, I call it a privilege because apparently here it's so rare. Back home, we burn trash almost on a weekly basis. It's time to burn the trash. Oh, mom. And you're out there burning the trash, just watching it burn. And then here I'm like, when do we burn trash? We don't. Okay. It's not legal. I'm like, okay. And then I realized I kind of miss burning stuff, right? But we do it in the lab in a safe environment. Anyway, so combustion is exothermic because when you're standing around a burning fire, you can feel the heat. It releases a lot of heat. Yeah, you're burning it, but it's the reaction itself is producing a lot of heat. For that reason, it's considered exothermic. Okay, so you can write the exothermic part using the symbol delta RH, and then you write the value negative 2855 kilojoules. The negative here implying it's exothermic, it's exiting the system, it's leaving, right? Or it's being produced. All the terms, they'll say heat is produced, right? Which also means heat, if you combine the heat value, the number, as part of the balance equation, that's okay. Heat will have to be a product. So heat will be a product in the exothermic reaction because it's produced. They say heat is released. Now I can't spell. Release, not released. Release. Or heat is formed. Or heat is lost. All of these are different terms to describe the same thing that's happening. The system decreases in the value of enthalpy. Heat is produced, it's released, it's formed, it's lost. Okay? And so if you want to incorporate the value of heat in kilojoules in the balance equation, it has to be a product. What about an endothermic reaction? Opposite is true. In this scenario here, our endothermic, the heat is coming into the system, so it's on the reactant side. Words such as heat required implies the reaction is not taking place until heat is applied, or heat added, or was burned. No, I should say burned. Heated. Okay. All these are trying to communicate that heat is being added to the system in order for the reaction to take place. You can write it this way, where the heat is a reactant in the endothermic reaction, reactant. And over here, you can write it this way, where it's not really part of the reaction. See, separate, and delta RH is positive, implying it's an endothermic reaction. So you can write it that way. Then finally, we have the scenario here. This is a question. Decomposition of limestone, a solid calcium carbonate right here, to lime, solid calcium oxide, and gaseous carbon dioxide is an endothermic reaction requiring the transfer of 178 kilojoules per mole of calcium carbonate decomposed. Okay, so we're given this equation right here, very interesting equation, and we're told it's endothermic, so we're given the amount of energy that's added, right? Oh, they're saying write the thermochemical equation in two forms. That was the charge. So it's decomposing, right? For decomposition reaction, I think I mentioned earlier. If I didn't, I'm mentioning it again. Calcium carbonate, when you're trying to figure out decomposition, it's not easy to just use switching ions to figure out what the product is. Just go ahead and use your textbook or other reliable resources to figure out what the complete equation is. CaCO3 decomposes and forms these two, but they do tell you what the products are, right? You have this product and you have that product. So you can write it in this form, or you can write the 178 as part of the balanced equation. Make sure the 178 is a reactant to communicate this reaction is endothermic. Okay. And then we have this general stoichiometric pathway. So what we're seeing here is there is a main pathway in stoichiometry. I want to call it the main road, okay? From mass to mass. Mass to mass conversion is the main road, okay? And you know how with any main road usually have side roads that kind of feed into the main road, and then there are roads that come from side roads that come from the main road. So I'm going to show you different pathways here. So you have the bright yellow pathway. I'm going to show you a pink pathway. And by the way, the yellow pathway shows you going from the left to the right or vice versa, right? I mean, correct. Now I'm going to show you the green pathway going from the energy, or the green looks like the, okay, let me use gray. Yeah, it looks much different. From that to that, okay, this pathway right here. You have the gray pathway possible. Then you have the pink pathway possible. Actually, you have a bunch of pathways, guys. Remember, chemistry is a problem-solving class, so we don't only study one way because we want to be able to handle, I want to say any problem, but we want to handle many problems that come along the way. So we don't prepare for one race. We prepare for all possible challenges we're going to face out there. So it took me a while to understand why we learned almost every scenario in chemistry. I used to hate that when I was in middle school. I'm like, oh, why are we learning another way of doing this? You know, when I was in elementary school, like, okay, we figured out one way. Why are we doing a different thing? I think I was too young to understand it was a problem-solving class. And with problem solving, the more skills you have, the more equipped you are to solve problems. As I took the class over and over again in upper level classes in high school and college, it started to click. Oh, we're learning different methods to handle different situations and problems, right? Okay, final question. Can you believe it? Final question here. Okay, I modified this question a little bit, and I'm going to show you where I modified it because it was just written in a convoluted way, okay? So the part I modified was this part right here. They gave you a conversion, and I modified this part. So I'm going to show you the original conversion. Let me erase that. We're told here what mass of liquid and octane, this is octane right here, a component of gasoline, must be burned. Burn means combustion reaction to transfer this amount of heat, okay? So before I even deal with this number, I write my balanced equation. I have my balanced equation here, okay? I want to talk about this number. At some point, they told us, which I took that out, so I'm going to add this back in, that 1 mole of C8H18, I'm trying to keep it simple for y'all, 1 mole of C8H18, when that is burned, when that is consumed, 1 mole produces, hold on a second, 10942, produces 5471 kilojoules of energy. They gave that information to us in the question. But when you balance out the equation, you don't end up with 1 mole. You end up with twice the number of moles of C8H18. So you have to adjust for that in the amount of heat, right? If you use more chemical, you get more heat. So you have to adjust for that. So essentially, I adjusted for that by doubling this number to get this, okay? So now I have so this is technically my given. This is my given number here, 9.05 times 10 power 4 kilojoules. So I have my balanced equation. This is my given number. So, okay, let's go back to stoichiometry, right? Let me move this out of the way. Remember stoichiometry, you want to find your two formulas that are important in the conversion. You want to find your given and label the given. You want to find your wanted and label the wanted. If you have more than one given, call it given 1, and then the other one given 2. And then, of course, you have wanted. You tend to have only one wanted, right? Okay. In this case, since we have this number here, this is not really a formula. This is our given. So I'm going to write here, given is equal to 9.05 times 10 power 4 kilojoules. Yeah, remember, as long as it's part of the balanced equation, any of the formulas, or in this case, the number, can be a given. And what's our wanted? This. And what do they want? Mass. When do they want it? I'm sorry. Now. Okay, so this is our given. So our stoichiometry will start from here and it will end right here. Okay, 9.05 is our given. Our wanted is mass in grams. So our stoichiometry path will be like this, like they showed here. From kilojoules to moles, we'll use a modified balanced equation conversion. We won't do a mole to mole relationship, we'll do a number to mole relationship. So it's kind of different than what we're used to. And then from here to here, we'll do a PT conversion. So y'all see how we did it, right? We started with a number, that's our given. And then we related this number, that this number, see, because it has to be on the bottom. These units have to match, right? So they can cancel out. This number here, I'll write it over again. I'll write it. Sometimes I hear y'all's voices. Can you write it over again? Okay. 9.05, just like we've learned before. Even though it's a new scenario, right? We're applying the skills we have, problem solving. Start with your given, and this is our given right here, right? I wrote it down. And then I have to do my conversion. I'm using my balanced equation conversion, but it's a modified version. So I call it MBE. I'm making up these acronyms, but it keeps me on track. Modified balanced equation. Balanced equation is when you're relating the amounts in the balanced equation, right? This number here, 10942. It has to go on the bottom because it's kilojoules, right? 10942 kilojoules, because they have to match diagonally. So this and this can cancel out. But that's the given, and related to the wanted, that's 2 of these. So you write 2, remember units, moles of C8H18. Okay. And, oh, they want us to get mass. So here I put the PT conversion as usual, 1 mole of C8H18. And that goes with the amount that I figured out earlier, 114 grams of C8H18. There. Moles and moles cancels out and we got grams. Now they can ask you the reverse where they give you grams and they ask you for energy, right? If they do that, you just go from grams to moles to kilojoules. Grams to moles, PT conversion. Moles to kilojoules, modified balanced equation. Just the reverse of what I'm doing, okay? So when you do the math, you can barely see 9.05 exponent. Ooh, can I see that? Oh, there it is. 4 times 2 times 114 divided by 10942. Oh yeah, I got the same number they got. 1886 grams of C8H18. And that is the end, my people. That is the end. Can you imagine? This is the end. Thank you for taking Chem 1405 with me. All the best with your other classes. Okay, I know that was very random. I felt inspired. Yay! And this is the last session, okay? So I hope this is helpful. I'll go ahead and stop the video. Hopefully it recorded. Yes, this is good. And we'll have no problems this time. No. Okay, I'll stop the recording.